So it's a beautiful sunny day and you go and enjoy that sunshine, and wait, that sunshine's really, really old. Let's take a quick look. But first, a shout out to Grace for being the 300th subscriber to the channel. Eilish, what do we say?
Good job, Grace. Good Grace, 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 good Grace.
And now back to sunlight. How do we get sunlight? Well, we got this thing called a sun. Here we go, shining in its lovely sunny gloriness. And we are here on Earth. That shouldn't be red. Let's make it blue. We're a blue planet. There we go. This is Earth. You know, it's got a big E. There we go. There's the Earth. Now, so we get our sunlight from the sun. That so far should be pretty straightforward. So the sunlight comes from the sun to the Earth. That takes a bit of time. Light is fast, but it's not instantaneous, right? It has a speed of roughly, and we're going to say roughly here, 300,000 kilometers every second. So we go per second, right? So remember, anything to the power of a negative indice just means that thing is on the bottom line. So s to the minus 1 essentially is the same as saying per s. There we go. But I like writing my units on one line. So there we go, the speed of light. Now, the sun's average distance from Earth is about 150 million kilometers. All right, average distance. The Earth goes around the sun not in a circular path, it's an ellipse. Sometimes it's a bit closer, sometimes it's a bit further, but average distance is about 150 million kilometers. Now, when you do the calculation on this one, that, how long does it take light to leave the sun's surface and get to the Earth? Well, we do the quick calculation. Let's do this right now. 1, 2, 3, 4, 5. We'll cut off 5 of those. There we go. We've now got 1500 divided by 3, and we come out at 500 seconds. Okay, so it takes light 500 seconds to reach the Earth from the sun. Now, wait, how long is 500 seconds? Well, let's do a quick conversion on that one. That's actually 8 minutes and 20 seconds, right? So 8 1/3 minutes. That's how long it takes light to reach the Earth. But it's way older than that. Let's take a look at how we got the light in the first place. Let's change color just because we can. Right, so the sun creates light in the core, and this is what's actually going on. 4 hydrogen atoms get combined into 1 helium atom. Now, it's not a one-step process. It's a lot more to it than this, but this is the overall. We started with the 4 hydrogens, we get 1 helium out the other end. The thing about this is that 4 hydrogens has a little bit more mass than 1 helium. Okay, basically 4 hydrogen atoms weigh more than 1 helium atom does. Let's take a quick look at a periodic table. Okay, here is the periodic table, or rather a couple of screenshots of a part of a periodic table. The 2 characters we're interested in are, of course, hydrogen on the far upper left and helium on the far upper right. The numbers we're interested in are these numbers here. These are the atomic masses of an average atom of these elements. So we can see that hydrogen has an atomic mass of 1.00794. Now we're going to ignore the 7. The 7 in brackets, that's actually the uncertainty, but we know for a certainty as far as the 4. Now the units for these are atomic mass units. Basically, it's so small. Come on, it's an atom. It really doesn't weigh much, right? So it's so small that we invented a new unit. We call it the atomic mass unit. And helium has a mass of 4, or just over 4 atomic mass units, AMUs. So let's look at what we're doing here. What we're doing is taking 4 of these hydrogens, right? So 4 times that, and seeing what the total mass is. So let's fire up a calculator. We have 1.00794, multiply that by 4 equals, that gives a total combined mass of, what have we got, 4.03176, 4.03176, and of course remember that's in atomic mass units. Now, the key thing to note now is that this number, 4 hydrogens, is actually greater than 1 helium. Okay, so when those 4 hydrogen atoms get combined, somewhere along the way, some mass is lost because the product, the helium, actually has less mass. Well, you can't just go and lose mass. That sounds a bit ridiculous, except that you can, of course, go and lose mass. Well, you haven't actually lost mass, you've converted the mass. I'm sure you've seen this equation right here. This is Einstein's very famous mass-energy equivalence formula. Einstein didn't actually say this. This is the simplified version, but it amounts to the same thing. What the deal is with this is that mass can actually be converted into energy. And likewise the other way, energy can be converted into mass. Okay, but we're talking, hey, at the moment we're missing some mass. Where did it go? It got converted to energy, right? Cool. Now, it was only a little bit of mass, right? The difference between the 4 hydrogens and the helium is a very small difference. But that's only 4 hydrogens, and this is being converted into 1 helium, but this is happening all the time, right? Really, really lots of hydrogens being converted to helium all the time. But anyway, if we just look at that 4 hydrogen atoms being converted into helium, the mass is very small. But remember, it's not just the mass, it's the mass times c. Now, c is actually the speed of light. Now, we've mentioned that before. That's 300,000 kilometers per second, right? Working in SI units, it's 300 million meters per second. So that's a really, really large number. Not only that, but it's the speed of light squared. So it's that little bit of mass multiplied by a really large number, multiplied by that same really large number again, gives us a lot of energy, which makes sense. The sun is a star. They put out heaps of energy. So let's draw what's going on. Here we have the core of the sun. This is where the nuclear fusion is actually occurring. Okay, so this is what we don't have. A photon gets released and woohoo, I'm out of here, I'm on my way to Earth. Yeah, that's not what's going on. What actually goes on is that the photon does get released and goes a little bit of a distance. Okay, now this diagram is so not to scale. The distance that photon travels is roughly 1 micrometer, so a millionth of a meter. That's really not very far. And then that photon gets absorbed by an adjacent particle, and another photon gets released, and maybe that next photon getting released goes this way, got absorbed, and then another one gets released, and maybe it goes this way, gets absorbed, gets released, goes this way, goes this way, goes this way. Now, what you can see here is kind of a random motion. We refer to this, well, mathematicians would refer to this as a random walk. Okay, in chemistry, we'd call this Brownian motion. A random walk is essentially a type of Brownian motion. Think like if you're walking down the mall and you walk past a candle store, right? Here's the candle in the store. Here's you walking down the mall. You're quite happy because you just smell this lovely smell. Well, the smell didn't go from the candle straight to your nostrils. The smell, actually, the fumes sort of went bouncing around through the air, and eventually, like it's quite a random path, but eventually that smell makes it to your nostrils and you think, nice smell. So that's Brownian motion. We'd refer to that in chemistry, right? So it's a random walk is what's happening to the photon. It doesn't just boog straight out to the surface of the sun and then, whoohoo, now I'm on a straight line to Earth. No. Once it gets to the edge of the sun, yeah, sure, then it's on a straight line. But to get to the edge of the sun, to the photosphere from the core, it's actually this random walk motion. Now, it does get to the photosphere. We know that because the sun does emit light. But it takes some time, even going at the speed of light, which we know is really, really fast. It still takes roughly 100,000 years. It could take more, somewhere around 100 to 170,000 years. Okay, so 100,000 years is at the lower end. So from the instant that photon is created, when the 4 hydrogens are converted to the helium, it takes about 100,000 years, plus, to get to the edge of the sun, and then it takes another 8 1/3 minutes to get to the Earth, right? Another 8 1/3 minutes on top of the 100,000 years that it's already taken. So sunlight is really, really old. Really old from our point of view, right? As you travel faster and faster, like approaching the speed of light type fast, time slows down. Time gets slower and slower. So if you're actually traveling at the speed of light, which the photon is, time actually doesn't pass at all. So as far as the photon is concerned, traveling at the speed of light, as soon as it was created, it reaches Earth. it reaches your eye and you can see, or it beats down on your skin and you can feel that lovely warm sunshine beating down on you, right? As far as a photon is concerned, it happened, boom, straight away. As far as we're concerned, yeah, that light is really, really old, 100,000 years and 8 minutes and 20 seconds old.
Don't forget to hit the like button. Yeah. And subscribe to It's Up Here. And here's another video.